Have you ever wondered if the very first spark of life might have begun on Mars, long before Earth was ready to hold it? Clues tucked into ancient meteorites and traces of lost Martian oceans hint at a story quietly more surprising than anyone expected. Tonight, here in the calm of Sleepy Traveler, we'll drift into that possibility and explore why some scientists think life may have started on a world now silent and red. No urgency and no firm conclusions, just gentle curiosity as you ease deeper into the dark. For now, let your breath soften. When you're ready, we'll follow the trail together, unhurried and warm. For a long time, people have looked at the stars and wondered how something as delicate as life could ever begin. Scientists give that wonder a quieter shape. They ask how simple, lifeless molecules could slowly learn to organize themselves into the intricate, self-copying systems we now call living organisms. And they ask why this extraordinary change seems to have taken root here on Earth. But as we learn more about Mars, another possibility sits gently at the edge of that question. Maybe our planet was not the first place where the story of life began. Maybe, in the very old days of the solar system, Mars was the older, calmer sibling, ready for life before Earth had even cooled. Because Mars is smaller, it lost its heat more quickly, while young Earth was still wrapped in oceans of molten rock and choking steam. Mars may already have worn a solid crust. That early stability made room for liquid water to gather on its surface, in valleys, craters, and low plains. Water, to life, is more than a simple liquid. It is a patient stage on which atoms can meet, connect, and rearrange. The air above that early Martian landscape was likely thicker than the thin, fragile atmosphere we see now. A denser blanket of gas would have trapped warmth, creating a gentle greenhouse effect that allowed water to remain liquid, not just in brief flashes, but in long-lived rivers, lakes, and perhaps shallow seas. The proof of that softer climate seems etched into the planet itself. Images from rovers like Curiosity and Perseverance show winding channels, fan-shaped deltas, and layered rock that look very much like sediments laid down by standing or flowing water. Each dried valley is like a faded photograph of a time when Mars was neither dry nor bitterly cold. If that world truly existed, it was more than beautiful. It was promising. A stable crust, long-lived liquid water, warmth, and time together form a kind of natural laboratory. In such a place, simple molecules do not just drift apart, they linger, interact, and slowly build complexity. Mars, in those early ages, may have been exactly that kind of laboratory. Its chemistry adds another quiet piece to the puzzle. Unlike Earth, Mars does not constantly recycle its surface through plate tectonics. Much of its ancient crust is still there, preserving the memory of the planet's youth. Locked in certain rocks and meteorites, we find elements that are especially important for life as we know it. Among them are phosphorus and boron. On Earth, these help build structures like RNA, a fragile but powerful molecule many scientists think may have carried and copied information in the earliest stages of life. Their presence on Mars hints that the red planet stocked its pools and shorelines with the right raw materials. Other ingredients are there as well. Mars is rich in minerals that contain iron, sulfur, and silica. On Earth, laboratory experiments show that when minerals like these are bathed in water and warmed gently, they can encourage simple carbon-based molecules to link up into more complex forms. Under a Martian sky, volcanic heat seeping through a mineral-rich crust and mixing with groundwater could have created countless hidden pockets of warm, reactive fluid. Each pocket a tiny, natural reaction vessel where chemistry might slowly have crossed the quiet border into biology. The discovery of organic molecules in Martian rocks by the Curiosity rover adds a soft but important note. Organic molecules are not proof of life by themselves, but they are the alphabet life tends to write with. Finding them tells us that Mars once supported a rich, active chemistry, capable of producing the complex carbon structures that living systems love to use. Still, even if life began there, another gentle question follows. How could anything that started on Mars ever have reached Earth? The answer draws us into the idea of panspermia, the thought that life, or its early precursors, might travel from planet to planet inside wandering rocks. In the youth of the solar system, collisions were common. Asteroids struck Mars with such energy that pieces of its crust were blasted into space. Some of those fragments drifted for long spans of time, circling the sun until they finally fell onto other worlds. Today, we have identified Martian meteorites on Earth. The gases trapped inside them match what we measure in the thin Martian air, like a quiet signature confirming their origin. On our own planet, we know of organisms called extremophiles, tiny forms of life that survive in conditions that would destroy almost anything else. They live in near boiling vents on the ocean floor, in frozen deserts, in acidic pools, in salt flats, where almost all water has gone. Experiments have shown that some microbes can endure intense radiation, long periods without water, and the near vacuum of space, especially if they are shielded inside rock. Put these pieces together, and a gentle, speculative picture appears. If simple, tough microbes arose on early Mars, some of them might have been buried deep within rocks when an asteroid struck. The rock around them could have softened the shock of the impact, protected them from heat, and then carried them out into space. They might have drifted in darkness for thousands or millions of years, sleeping through cold and silence until gravity pulled their stone capsule down through Earth's atmosphere. If even a few survived the fall and woke up in a warmer, wetter world, they could have been the first ancestors of everything that now lives here. If this is true, Earth is still a world rich with its own stories, but it is not the very first chapter. Our biosphere would be part of a longer tale that began under a smaller sunlit sky on dusty plains beside Martian rivers. In that view, life is less a miracle that happened once in one perfect place and more a natural outcome when the right conditions gather together, capable of traveling and taking root in new homes. Such a possibility gently unsettles the old habit of thinking about Earth as uniquely blessed. For a long time, it was easy to imagine our planet as the single bright island of life in an endless, empty sea. But if life here began with a gift from Mars, or if both planets shared the same scattered seeds, then life becomes something the universe may do often, not rarely. Skeptical voices remind us that the evidence is far from settled. They point out that Earth itself is an extraordinary engine for chemical change. Its active geology, constant volcanism, deep oceans, lightning storms, and cycles of wet and dry created many different environments where life could have emerged on its own, without help from beyond. In that view, Mars was interesting, but Earth, with its restless heart and shifting surface, remains the likeliest cradle. Yet even that cautious view does not push Mars out of the picture. In the early ages of the solar system, Earth and Mars were not strangers. They were neighbors in a shared storm constantly exchanging material. Rocks struck from one world sometimes found their way to the other, whether those stones carried living passengers or only complex molecules. They tied the fates of the two planets together. To understand how deep that connection may run, it helps to picture the solar system in its earliest, wildest time. Our sun was young then, newly lit at its core, surrounded by a swirling disk of gas and dust. Within that disk, tiny grains collided and stuck together, becoming pebbles, then stones, then larger bodies called planetesimals. With each collision, heat was released. In some of these growing worlds, rock melted, and heavier elements like iron sank inward, while lighter materials floated up. Over long stretches of time, these planetesimals merged and shattered, and merged again, slowly becoming the rocky planets we know: Mercury, Venus, Earth, and Mars. It was not a gentle process. Worlds collided. Some were broken apart, others grew larger with each impact. Out of that chaos, Earth and Mars took shape and began to follow their own paths. One quiet but crucial difference between them was size. Mars, being only about half as wide as Earth and far less massive, cooled more quickly. Its molten seas of rock hardened sooner, and a solid crust formed, while Earth still glowed with internal heat. That early stability allowed water, delivered by comets and asteroids, or released from within, to condense and settle on the surface. Lakes could form, rivers could carve channels, maybe even an ocean could collect in the lowlands. Earth, with more mass, held on to its heat. Its surface stayed molten and unstable for longer. While Mars may have already had basins filled with liquid water under a softer sky, Earth remained wrapped in scorching rock and dense, shifting clouds. Volcanic eruptions released gases that slowly built up a thick atmosphere, but it took a long time for the surface to cool enough for stable oceans to form. This difference created what some scientists call an ancient habitability window for Mars. There was a period in the distant past when Mars may have been more hospitable to life than Earth was. During that time, its rivers could flow steadily, its lakes could persist, and its climate, though not as gentle as Earth's later became, might have been mild enough for long-lasting liquid water. The traces of that era are still visible on the Martian surface: dry riverbeds, layered sediments, and deltas where water once slowed and spread its load of silt. Meanwhile, both planets were being shaped by visitors from the outer solar system, asteroids and comets. Rich in water and organic molecules bombarded the inner worlds again and again. When they struck, they not only carved craters but also delivered water and carbon-based compounds, stirring the chemical pot on any planet they touched. Mars, sitting closer to the asteroid belt, may have received a slightly different blend of these materials than Earth, giving its early chemistry a distinct flavor. The impacts did something else as well. Each large collision generated brief but powerful bursts of heat. Rock fractured, water melted, and hot, mineral-rich fluids flowed through the subsurface, creating temporary hydrothermal systems. On Earth today, places like that are vibrant with life. On early Mars, they may have offered sheltered, energy-rich environments where simple molecules could combine into more intricate forms, protected from harsh radiation at the surface. Earth's earliest history was likely even harsher. The rate and violence of impacts may have been high enough to repeatedly boil away oceans and sterilize large regions of the surface. Any fragile early life might have been wiped out many times before conditions settled. Mars, with its smaller size and perhaps calmer early climate, may have enjoyed stretches of relative peace where delicate chemistry could persist. Around roughly 4 billion years ago, the inner solar system appears to have passed through a particularly intense phase, often called the Late Heavy Bombardment. Asteroids and comets rained down in great numbers, reshaping the surfaces of the rocky planets. For Earth, this time may have delayed the emergence of stable, long-term habitats, but it also added more water and organic material to the planet's surface, enriching it for the future. Mars, with its thinner atmosphere and weaker gravity, was also scarred by this barrage. Many of the craters from that time remain visible because Mars lacks the active plate tectonics that constantly erases Earth's oldest marks. By studying those scars, scientists learn not only about impacts but also about how the planet responded. Some wonder whether the late heavy bombardment, destructive as it was, might have provided Mars with a final burst of energy and ingredients, helping it move from being merely habitable to possibly inhabited. If life did take hold during Mars's early window of habitability, the same impacts that scarred its surface could have become the vehicles for sharing that life. Rocks blasted into space, carrying tiny passengers hidden within, could have drifted outward or inward, eventually falling on Earth. This specific version of panspermia, where life travels inside solid rock, is often called lithopanspermia. In that quiet, speculative story, Mars is the first cradle, and Earth inherits its living legacy. Today, Mars is a far colder, drier place. Its rivers have long since dried up. Its lakes and possible oceans have vanished into ice and thin air. Much of its atmosphere has been stripped away by the solar wind. Dust storms wander over empty plains, and the nights are bitter and still. Yet beneath that quiet surface, the evidence of its warmer, wetter past remains, written in stone and frozen in mineral veins. Our robots trace those stories grain by grain, and one day humans may walk there to read them with their own eyes. What they find will not only tell us about Mars, but also about ourselves, about where our deepest roots may lie. For now, we are left with a gentle, lingering image of that young world. Rivers under a pink sky, lakes in wide basins, a crust rich in the elements of life, a planet that, in a distant age, may truly have been what the phrase suggests in a whisper. Mars, an ancient oasis. Mars has always felt like a world half awake in our imagination, not just a red light in the sky, but a place that might once have carried its own quiet kind of life. The planet we see now is cold and dusty, wrapped in a thin, fragile veil of air. Yet, when we read the stories etched into its surface, a different Mars appears beneath the sand, one rich in water and change, a world that may once have been gentle enough for life to find a foothold. If you float in your thoughts above that ancient landscape, you can trace long valleys wandering across the terrain, the paths of rivers that no longer flow. These winding channels and branching networks look very much like dried-up river systems on Earth, the kind carved slowly by liquid water that runs not for moments, but for ages. They hint that water on Mars was once steady and persistent, not just a brief visit from melting ice. Inside great impact basins like Gale and Jezero, the evidence grows even more intimate. There you can see fan-shaped deltas, places where rivers once slowed and spread as they entered long-vanished lakes. Layer upon layer of fine sediment settled there, building up over time and keeping a careful record of changing waters. Such lakes would have been calm, nourishing environments, rich in minerals and with gentle shorelines where simple microbes, if they ever arose, might have had room to grow and drift. The surface holds many other signs of a watery past. Alluvial fans, built from debris, washed down slopes, point to episodes of flooding when sudden surges of water carried rocks and dust outward and then let them fall in graceful spreads. Even old craters, born from violent impacts, show softened rims and carved channels, as if water later moved through them and slowly wore away their sharper edges. In more recent observations, narrow, dark streaks have been seen creeping down certain slopes and then fading again with the seasons. These recurring features might be traces of salty water that briefly seeps to the surface before vanishing. Taken together, all of these hints draw a single, vivid picture. There was a time when Mars was not a frozen desert, but a world where water was abundant, moving, and deeply involved in shaping the land. For such a world to exist, Mars must once have had a very different climate. Today, it is bitterly cold, and liquid water on the surface would almost immediately freeze or evaporate. Long ago, though, the planet appears to have been warmer and wetter, with conditions that allowed water to remain liquid for long stretches of time. The young sun shone more weakly than it does now, but Mars had help from its own interior. Volcanic eruptions would have released great amounts of carbon dioxide and water vapor into the air, building up a thicker atmosphere that trapped heat in a gentle greenhouse blanket. Climate studies suggest that ancient Mars may have cycled between drier times and wetter ones, with periods of rainfall or snowmelt that filled rivers and lakes. Volcanic activity, by sending ash and gases into the sky, could have periodically warmed the planet, melted ice, and set water flowing again over the surface. In those eras, the atmosphere would have been far denser than the thin whisper that surrounds Mars today, dense enough to support surface pressures where liquid water could exist out in the open. That thicker atmosphere did more than just hold warmth. It also helped shield the surface from harsh cosmic radiation, creating pockets of relative safety where delicate molecules and perhaps even living cells could survive. In that protective calm, water and rock had time to interact, dissolving minerals, carrying elements, and setting the stage for complex chemistry. At some point, though, Mars began to lose this protection. Its magnetic field, which had once helped guard the atmosphere from the constant stream of charged particles flowing from the sun, weakened and faded. Without that shield, the solar wind could strip away the upper layers of the atmosphere, bit by bit. Over long spans of time, the air grew thinner, the greenhouse effect weakened, and the surface cooled. Liquid water retreated into ice, and perhaps into underground reservoirs, and the open lakes and rivers disappeared. Before that fading, the planet may have carried truly vast bodies of water. Many researchers suspect that the northern lowlands once held a wide ocean that wrapped around a large portion of the hemisphere. Ancient shorelines traced in the topography curve like the edges of lost coasts, and certain deposits along those lines resemble sediments laid down by waves on a beach. If such an ocean existed and remained for millions of years, it would have been a vast and varied habitat for any early life. Even after the surface froze, water did not simply vanish from the story. It sank into the ground and locked itself into ice, Radar studies and rover findings have revealed thick layers of subsurface ice and buried glaciers, relics of the planet's wetter past, preserved beneath dust and rock. Some of these icy deposits lie in the polar regions. Others are tucked away at lower latitudes, close to places where humans may one day walk. There may even be ancient aquifers, pockets of liquid water trapped and insulated below the surface, hidden away from the biting cold and radiation above. If life ever found a home on Mars, such underground refuges might still shelter it. To grasp how remarkable this is, it helps to compare Mars to our own planet in its earliest days. Both worlds began with similar ingredients: volcanic fires, water, and a store of essential elements like carbon, hydrogen, nitrogen, and phosphorus. But their stories parted ways because of their different sizes and internal lives. Earth, larger and more active, developed shifting tectonic plates that continually recycle carbon dioxide between air, ocean, and rock, smoothing out extreme swings in climate and keeping a long-term water cycle running. Mars, smaller and cooling more quickly, seems to have lost such deep internal motion earlier in its history. Without moving plates to regulate its atmosphere and climate, the planet had a shorter window where stable, surface water could persist. Yet during that window, its lakes, deltas, and river systems looked strikingly similar to environments on early Earth where microbial life flourished. The clays and layered sediments found in Martian craters are close cousins to deposits from Earth's own deep past. That resemblance suggests that if life can take hold in such settings here, it might well have had an opportunity to do the same there. The record of water is not only written in shapes, but in minerals. Across Mars, rovers and orbiters have found hydrated minerals such as clays and sulfates, which form only when water and rock interact over long periods. Their presence shows that water was not just splashed briefly across the surface. It lingered, pooled, seeped through the crust, and left durable traces of its passage. Other minerals add more detail. Certain deposits rich in silica and iron oxides tell of water that was neutral or only mildly acidic, conditions that on Earth can be very welcoming to microbes. Some soils contain salts that likely came from briny, concentrated water that evaporated and left its dissolved load behind. Each of these minerals is a small, solid anchor for the idea of a Mars that truly was, for a time, a watery world. Volcanic activity intertwined with this water history as well. When volcanoes erupted, they did not just pour out lava, they also released gases and steam, enriching the atmosphere and feeding chemical reactions in the air and on the ground. Where heat from below met water from ice or buried reservoirs, hydrothermal systems likely formed, with hot, mineral-rich water circulating through fractures and pores in the rock. On Earth, such systems at the bottom of the sea and in volcanic regions are considered promising places for life to begin or to find refuge. On Mars, they may have served a similar role, acting as natural chemical workshops where simple molecules could be energized and assembled into something more complex. Even as the planet dried, water did not vanish everywhere at once. Different regions kept it for longer or lost it sooner. The high southern uplands may have held small glaciers and seasonal snow, while the lower northern plains collected lakes and perhaps remained wet for longer. The planet's tilt and orbit changed over time, shifting where ice could be stable and how much sunlight reached different latitudes. Dust storms likely moved thin films of water vapor around, affecting where frost formed and melted. For a long while, water may have cycled between surface, subsurface, and sky, even as the general trend slipped toward cold and dryness. This long, intricate story of water is not just a piece of planetary trivia. It is the background music for a deeper question. Did Mars ever move from rich chemistry to actual life? To approach that, we listen not only to water, but to the faint whispers of organic chemistry on the planet. In recent years, one of the most meaningful discoveries has been the detection of organic molecules in Martian rocks. The Curiosity rover, working in Gale Crater, drilled into ancient mudstones that formed at the bottom of a long, vanished lake. Inside those rocks, it found a variety of simple organic compounds, including ring-shaped molecules containing sulfur and long chain-like hydrocarbons. These are not themselves living things, and they do not prove that life was present, but they are the kind of molecules that life tends to build with, the basic pieces from which more complex biological structures can be assembled. Their presence is important for two gentle reasons. First, it shows that the chemical ingredients needed for life existed on Mars billions of years ago. Second, it tells us that those ingredients could be preserved in rocks for immense stretches of time, shielded from the worst of radiation and oxidation. The organics Curiosity found might have come from biology, from meteorites delivering carbon-rich material, or from purely geological reactions. Regardless of their origin, they widen the door to the possibility that Mars once hosted a chemistry capable of stepping toward life. Above the ground, another clue drifts in the thin air: methane. On Earth, methane is often associated with life, produced by microbes, wetlands, and other biological activity. On Mars, instruments on the surface and in orbit have detected faint traces of methane that seem to vary with time, rising and falling in ways that suggest the gas is being released from somewhere beneath the surface. The source of Martian methane is still unknown. It could be made by non-biological processes, such as reactions between water and certain types of rock deep underground. It could also be influenced or produced by microbes, if any survive in hidden niches below the surface. What makes methane especially intriguing is that it does not last long in the atmosphere. Sunlight and chemistry break it down, so any methane we see must have been released fairly recently, at least in geological terms. That implies that Mars is not completely still on the inside. Something, whether rock or life, is still active. The chemical richness of Mars is also written in more challenging characters. One of these is the family of compounds known as perchlorates, reactive salts that include chlorine and oxygen. These were first clearly identified in Martian soil by a lander that heated samples and watched which gases were released. Perchlorates pose a serious challenge for our search for organics. When soil that contains them is heated in an instrument, the perchlorates can break apart delicate organic molecules before we can identify them, turning them into simpler gases and leaving us unsure of what was originally there. Yet, as so often happens in this story, what seems like an obstacle may also be a quiet hint of possibility. On Earth, certain extremophile microbes can actually use perchlorates as a source of energy, metabolizing them in ways that let them survive in harsh, salty, and dry conditions. If anything similar ever evolved on Mars, these reactive salts could serve as a kind of fuel, helping life persist in cold, shielded corners of the subsurface. In this way, perchlorates become a paradox at the heart of our search. They make it harder for our instruments to see the organic traces we are looking for, burning away the very signatures we hope to read. At the same time, they might also represent a potential lifeline for any hardy organisms that once found or still find a home on the red planet. When we look back into the deep past of Mars, we find a world shaped not only by water and minerals, but by forces that once wrapped it in protection. Long ago, the red planet carried a magnetic field, a soft but powerful shield that guarded its surface from the sun's harsh winds. Beneath that invisible shelter, delicate organic molecules could form and settle into the soil without being immediately torn apart by radiation. It was a time when the planet still held on to its breath, its atmosphere thick enough to cradle warmth and chemistry. But that shield did not last forever. As Mars cooled inside, its magnetic field weakened and slowly faded. Without that invisible armor, the planet's atmosphere was left bare to the constant stream of solar particles. Over ages, the solar wind stripped away the air, carrying off the gases that once held warmth close to the ground. Cosmic rays reached the surface with increasing intensity, breaking apart fragile organic molecules and leaving the land more barren with every passing era. What survived would have been pushed downward, slipping into the safety of rock and dust. Today, if any organics remain on Mars, they are likely hidden far beneath the surface, tucked into layers of regolith, or sealed within rocky cracks that shield them from radiation. These underground spaces, cold and quiet, might hold the last whispers of what once was. They are the places future missions will listen to most closely, drilling gently into the crust in hopes of uncovering what remains preserved in the dark. Mars also carries the memory of hydrothermal warmth, places where heat from the interior once pulsed upward into water-rich crust. Evidence suggests that ancient hydrothermal vents dotted the planet, forming pockets of warm, mineral-rich water. Here, chemical reactions could unfold at their own steady pace, nourished by energy rising from below and minerals swirling through the water. On Earth, such places teem with life, entire ecosystems thriving without sunlight. It is natural to imagine that similar vents on Mars, long ago, could have served as gentle incubators for early chemistry, or even for life itself. Across the planet, another stream of organic matter arrived from the sky. For billions of years, Mars has been struck by meteorites, especially carbon-rich ones that carry amino acids and other building blocks of life. Each impact would deliver a fresh scattering of organic compounds onto the surface, adding to the natural inventory of molecules already forming there. The heat and pressure from large impacts can also create new compounds, forging organics in the blink of a geological eye. Craters like Gale and Jezero are therefore not only scars from ancient collisions, but places where chemistry may have been stirred and altered in powerful ways. Among the mysteries Mars still holds is the strange connection between oxygen and methane in its thin atmosphere. Over several Martian years, the Curiosity rover recorded seasonal rises and falls in both gases. On Earth, such paired changes often hint at biological activity, though that does not have to be the case. Sunlight can trigger complex photochemical reactions in the air, creating or destroying methane without life being involved. Still, the rhythms Curiosity observed remain puzzling, and their meaning is not yet clear. If nothing else, these changes remind us that Mars is not a perfectly silent planet. Its chemistry still breathes in ways we do not fully understand. Yet finding organics on Mars remains one of the planet's most stubborn challenges. Its soil is full of oxidizing substances like perchlorates, reactive compounds that easily destroy organic molecules when heated or exposed to strong radiation. Instruments meant to detect delicate compounds must tread lightly, separating true Martian chemistry from Earth-based contamination, while also distinguishing biological patterns from non-biological ones. Missions like Perseverance and the long-awaited Mars sample return aim to collect untouched samples and bring them home for the most sensitive study humanity can attempt. Beneath the planet's red dust lies a rich collection of minerals, phosphates, boron, sulfur, iron, each one offering something essential to the chemistry of life. At the center of life as we know it is RNA, a molecule built on a sturdy backbone of phosphate. Mars seems to possess plenty of phosphate-bearing minerals, including apatite, found in meteorites and rocks, studied directly by rovers. When these minerals dissolved in ancient Martian lakes and streams, they may have released phosphates in abundance. Some scientists think Mars may even have offered more accessible phosphate than early Earth, simply because its waters were more acidic and could dissolve these minerals more easily. Boron adds another layer to this quiet story. Curiosity detected boron in Martian rocks within Gale Crater, a discovery that surprised many. Boron helps stabilize ribose, the sugar at the heart of RNA, keeping it intact long enough for more complex chemistry to unfold. On early Earth, boron was likely rare and unevenly distributed, but Mars, shaped by volcanic activity and unique mineral mixtures, may have provided more accessible borates. It invites the gentle question: did Mars offer friendlier conditions for life's earliest molecules than our own planet did? Iron, which colors the Martian soil in warm reds and browns, is more than a pigment. It is a catalyst, capable of driving reactions that generate amino acids and other essential organic compounds. Ancient Martian waters likely carried dissolved iron, creating settings where molecules could form, break, and reform in rich chemical cycles. These iron-rich environments resemble, in some ways, the hydrothermal vents on Earth, where many researchers believe life may have begun. Sulfur is just as significant. Mars has abundant sulfur in the form of sulfates and sulfides, minerals that can drive reactions central to metabolism, enzymatic activity, and the synthesis of proteins. Sulfur dissolves readily in water, creating reactive solutions that could have nurtured early chemistry. Volcanic eruptions on Mars would have sent sulfur into the air and into ancient lakes, forming hotspots of chemical activity much like the sulfur-rich vents on Earth's ocean floor. Silicon, a major ingredient in many Martian rocks, adds its own quiet support. Silicate minerals like quartz and feldspar provide surfaces where molecules can gather and interact. They act as natural concentration tables, where organic molecules can stick, settle, and eventually form more complex structures. Water flowing across volcanic landscapes would have brought silicates into contact with dissolved organics, creating environments where fragile chemistry might linger long enough to evolve. Among the most meaningful minerals on Mars are its clay deposits, broad expanses of phyllosilicates found in regions like Gale and Jezero. Clays are thought to have played an important role on early Earth, acting as catalysts that help small molecules join into larger ones. Their layered structures can trap organics, concentrate them, and shelter them from harsh conditions. On Mars, ancient rivers and lakes left behind vast fields of clay, where early chemistry might have been nurtured and protected. What makes Mars especially precious is its geological stillness. While Earth's crust has been endlessly recycled by tectonic plates, Mars has remained relatively unchanged for billions of years. Much of its early mineral record, shaped in ages when life could have begun, is still preserved exactly where it formed. It is a time capsule of the early solar system, a place where old minerals and ancient chemical reactions have waited quietly for us to notice them. One of the most extraordinary gifts Mars has sent us are its meteorites, small fragments of its crust that were blasted into space by powerful impacts before eventually landing on Earth. We have found fewer than 300 of these rare stones, each one carrying a chemical fingerprint that matches the Martian atmosphere measured by early landers decades ago. These rocks are messengers, carrying pieces of Mars's history across time and space. The most famous among them is a meteorite found in Antarctica in 1984, known as ALH 8401, estimated to be more than 4 billion years old. It holds tiny, rounded structures that once sparked immense excitement. In 1996, researchers announced that these features might be microfossils, or chains of magnetic minerals similar to those produced by certain bacteria on Earth. For a moment, the world wondered whether this rock held the first solid evidence of life beyond our planet. But skepticism soon followed. Some scientists argued that these features could have formed without life, or even after the meteorite landed on Earth. Over time, more studies have deepened the debate, but not resolved it. Whatever its true origin, ALH 8401 remains an important clue, an artifact from a time when Mars was young, warm, and full of possibility. Each Martian meteorite begins its journey in violence. Asteroids and comets strike the red planet, releasing enough energy to send pieces of rock flying into space. Because Mars has lower gravity and a thinner atmosphere than Earth, it is easier for such fragments to break free. After drifting for ages through the solar system, some eventually cross Earth's orbit and fall to the ground, bringing with them traces of Mars's minerals, water, and even organics. Their existence naturally raises a question that feels both ancient and new. Could life have begun on Mars and then arrived on Earth by traveling inside these rocks? Experiments have shown that microbes buried deep within stone can survive the intense heat of atmospheric entry, as well as the cold and radiation of space. If life existed on Mars during its habitable era, meteorite transfer could have served as a bridge, carrying Martian organisms to a warmer world where they flourished. Or perhaps the journey happened the other way around. Scientists classify Martian meteorites into several groups: younger volcanic rocks, older water-altered stones, and rare samples from deeper mantle regions. Each type reveals something different about the planet's past: its lava flows, its interactions with water, its interior composition. Together, they tell of a world that once had erupting volcanoes, flowing water, and air thicker than the fragile breath it holds today. Among these samples, some contain organic molecules, simple carbon-based compounds that excite the imagination. One meteorite in particular, ALH 88401, has organics whose isotopic fingerprints suggest they formed on Mars itself. The pattern of isotopes ratios of certain carbon and hydrogen points toward processes native to the red planet. Yet, contamination from Earth can never be entirely ruled out, and every attempt to interpret these precious samples walks a delicate line between hope and caution. Because of this, Mars's meteorites remain both a gift and a riddle, objects that hold pieces of ancient chemistry, but also remind us how difficult it is to separate what is Martian from what is earthly. Their isotopic signatures deepen the mystery, even as they draw us closer to understanding a planet that has been whispering its secrets across the void for billions of years. Beyond the question of whether anything ever lived there, the stones from Mars tell us about the world that shaped them. Inside Martian meteorites, tiny pockets of gas are trapped like time capsules. Their composition matches the ancient air of Mars, showing that the planet once carried a thicker atmosphere than the whisper of gas it holds now. Water-altered minerals inside these rocks speak of contact with liquid water, hinting at rivers, lakes, and perhaps even gentle rain that fell on a younger, softer Mars. These clues line up with what orbiters and rovers have been seeing on the surface for years: dried river valleys, deltas fanning into craters, layered sediments laid down by standing water. Together, meteorites from Earth's deserts and ice fields and images sent from the Martian sky tell the same quiet story. Long ago, Mars seems to have shifted from warm and relatively humid to cold and dry. Volcanic eruptions changed its air. Its magnetic shield faded, and the solar winds slowly peeled away its atmosphere. Piece by piece, that transformation turned an active, watery world into the frozen desert we see today. Studying these traveling rocks is delicate work. Martian meteorites are rare, and their long journey through space and time has altered them in subtle ways. Once they land on Earth, they begin to interact with our own water, air, and life. Tiny traces of terrestrial contamination can creep into cracks and surfaces, hiding or mimicking Martian chemistry. Even within the stones themselves, it can be hard to tell which features formed on Mars, which formed in space, and which are the results of their fall through our atmosphere. Despite these complications, new techniques keep opening their secrets. Modern spectroscopic methods let scientists look at the mineral structure and chemistry of meteorites in exquisite detail, picking out patterns that once would have gone unseen. Behind every spectrum is a quiet question. What was the world like where this crystal first grew, where this tiny bubble of gas was trapped? The answers matter, not only for understanding Mars, but for planning how we will explore it. Meteorites help guide where rovers should land, which minerals they should search for, and how we might recognize true signs of past life. They also prepare us for what returned samples from Mars itself may look like when, someday, we hold them in our laboratories. The story they tell is far from finished. As more meteorites are found and studied, the hazy outline of Mars's past grows sharper, one grain at a time. Wrapped around all this is a larger, almost dreamlike idea. Maybe the story of life on Earth did not begin here at all. Maybe its first chapter was written somewhere else, and then delivered, quietly, across space. This is the heart of the panspermia hypothesis, the notion that life, or at least its earliest seeds, can travel between worlds. The word panspermia means seeds everywhere, and the idea has roots deep in human thought. Long before rockets and rovers, ancient philosophers imagined life sprinkled through the cosmos. Many centuries later, more modern thinkers suggested that microscopic organisms could be carried between planets, pushed by light, or drifting on particles of dust. Over time, the idea branched into different forms. Lithopanspermia imagines life traveling inside rocks. Radiopanspermia considers tiny spores borne along by radiation pressure. Directed panspermia wonders whether an advanced civilization might someday choose to spread life deliberately. For a long time, these ideas felt more like philosophy than science. But as we built spacecraft, particle accelerators, and more careful experiments, they began to be tested in small, concrete ways. Organic molecules were found on comets. Meteorites were shown to carry amino acids. Tiny creatures from Earth hurled into conditions like those in space sometimes survived in ways that surprised us. And then, of course, there were the Martian meteorites, bearing hints of organics and water from another world. Space is not a gentle road for any traveler, especially something as fragile as life. In the vacuum between planets, temperatures swing between searing sunlight and deep cold, and radiation from stars and galaxies passes through almost everything. Yet on Earth, we keep finding organisms that seem almost designed for such hardship. There is a bacterium, often called the toughest on Earth, capable of withstanding radiation doses that would be instantly lethal to humans many thousands of times over. There are tiny creatures known as water bears, or tardigrades, that have survived being exposed to the vacuum of space and still woken up when returned to gentler conditions. Experiments aboard space stations and in specially designed satellites have taken spores and cells, exposed them to space-like conditions, and then brought them back to see which ones endure. Some do, especially when they are shielded inside layers of rock or ice. It is as if life, once it appears, carries within it a stubborn ability to cling to existence, even under circumstances that seem impossibly harsh. The mechanics of panspermia depend on more than just toughness, though. There must be a way for material to leave one planet, travel through space, and land on another without everything being destroyed. Here, cosmic impacts play their part. When a large asteroid or comet strikes a planet, the energy released can launch fragments of rock into space at great speeds. On a world with lower gravity and thinner air, such as Mars, it is easier for pieces to escape entirely and set off on long, looping journeys around the sunday. Simulations show that fragments of Martian rock, possibly containing dormant microbes or complex organics, could be flung clear of Mars and eventually cross Earth's orbit. Some of those fragments would be captured by Earth's gravity and fall as meteorites. The fact that we now hold real Martian rocks in our hands is proof that this exchange of material does happen. The question left hanging in the air is whether anything living has ever made that trip. Timing adds a gentle twist to the story. Mars cooled and settled down earlier than Earth did. It may have reached a stable, habitable state, while our planet was still being battered and sterilized by frequent impacts. If life arose on Mars first, fragments of its crust carrying hardy organisms could have reached Earth within tens of thousands of years, a brief span in planetary terms. Other pieces might have drifted for millions of years in stable orbits before finally falling. Each stone would be a small, natural spacecraft, insulated against temperature swings and shielding its interior from much of the radiation outside. Of course, the journey through space is not the only trial. There is also the fierce heat of entry into a planet's atmosphere. Yet, meteorites often show that their cores remain relatively cool, while only their exteriors melt or char. Experiments with microbes embedded deep inside rocks suggest that some could survive both the launch and the landing, so long as they are well hidden within. Not everyone is convinced, and skepticism is part of the quiet honesty of science. We have not yet found direct proof of life on Mars or in any meteorite. Features that look like fossils can often be explained by non-living processes. Organic molecules might be formed by purely chemical reactions. Critics of panspermia argue that until we actually find living or clearly fossilized organisms from another world, the idea of life traveling between planets remains speculation. Yet even the critics usually agree on one thing: the ingredients of life are mobile. Comets carry organic molecules. Meteorites deliver carbon compounds to planets. Space is not entirely empty. It is full of dust and ice that can act as both carriers and catalysts. If nothing else, panspermia may describe how the raw materials for life are shared throughout a planetary system. The idea does not have to stop with Mars and Earth. Icy comets, with their reserves of water and organics, may have spattered many worlds with the same seeds. Moons like Europa and Enceladus, with oceans beneath their ice shells, may trade material through impacts and plumes of vapor. If life exists in those hidden seas, pieces of it might occasionally be thrown into space, just as Martian debris has been. In that picture, the solar system becomes less a collection of isolated worlds and more a quiet network through which matter and perhaps life can flow. Directed panspermia adds a more speculative, almost philosophical layer. It suggests that an advanced civilization might someday choose to guide life intentionally, sending spores, engineered microbes, or genetic material to other planets to help life begin or continue there. There is no evidence that this has ever happened, but the idea raises questions about our own future. If we ever face the end of life on Earth, would we try to send a biological message in a bottle out into the cosmos, hoping it would someday wash ashore on another world? Such questions are not only imaginative, they can be made testable. If we ever find life elsewhere that carries strange, non-natural patterns in its molecules, or unusual ratios of isotopes that do not match normal planetary chemistry, we might wonder whether it was shaped by intelligence rather than by blind chemistry alone. At its core, panspermia gently challenges the idea that life had to start here, on this one planet, entirely by itself. It suggests, instead, a universe where life and its building blocks may be shared, passed along like embers between stones in a long, slow fire. In such a universe, the appearance of life on Earth might not be an isolated miracle, but one bright point in a much larger constellation of living worlds. To understand how Mars fits into that constellation, it helps to compare its early story with our own. Both Mars and Earth formed from the same swirling cloud of dust and gas around the newborn Sunday. Over time, collisions built them up into full planets, but their sizes, their distances from the sun, and their internal rhythms led them down different paths. Mars, being smaller and farther out, cooled more quickly. Its crust solidified and its surface calmed, while Earth was still roiling with molten rock and heavy bombardment. Geological clues suggest that Mars entered a relatively stable, habitable phase very early, with liquid water on its surface and a thick enough atmosphere to hold that water in place. Earth's early days were harsher. For hundreds of millions of years, it was a world of fire and storms, hammered by large impacts and wrapped in choking gases. Only after this violent youth began to quiet did oceans form and stabilize. That lag means Mars may have had a head start, a window of time when it could support life while Earth was still unready. On Earth, the earliest clear evidence of life comes from layered structures called stromatolites, formed by mats of microbes in shallow waters billions of years ago. These ancient communities show that life, once it appears, can find ways to adapt, even to harsh conditions. Strong ultraviolet light, limited oxygen, shifting temperatures. The microbes that built those structures were early masters of survival. Mars, during its own early habitable window, seems to have offered environments that could have appealed to similar hardy organisms. There were flowing rivers, broad lakes, and perhaps an ocean in the northern lowlands. Volcanic and hydrothermal activity provided heat and chemical energy. Iron and sulfur compounds in the soil could have supported microbes that fed on chemistry rather than sunlight. If life ever began there, it might have looked very much like the small, tough extremophiles that still thrive in Earth's most extreme places. Water, for both planets, is the quiet foundation of all of this. Earth's wide oceans cradled early life, shielding it from radiation and giving it a stable medium in which to react and grow. Mars did not have oceans on the same scale, but its ancient river valleys, lake beds, and deltas are carved deeply enough to tell us that water once moved across its surface in great amounts. The crucial question is how long that water remained liquid and whether it persisted long enough for life to take hold and evolve. Mars's smaller size and weaker gravity made it harder for the planet to hold on to its atmosphere over billions of years. As its magnetic field waned, the solar wind stripped away more and more of its air. Surface water evaporated or froze, yet not all of it vanished. Ice still lies beneath the surface in many regions, and hydrated minerals still carry traces of water locked into their structures. These hints suggest that liquid water may have lingered underground even after the surface became inhospitable. Life needs energy as well as water. On Earth, early organisms drew that energy from sunlight, from chemical reactions, and from the heat of the planet's interior. Chemosynthetic microbes, in particular, learned to live by pulling energy from reactions involving sulfur, iron, and hydrogen, thriving in places like deep-sea vents and hot springs where sunlight never reaches. Mars, too, had volcanic and hydrothermal activity that could have created such environments. Hot springs, vents, and warm, mineral-rich waters beneath the surface could have been nurturing grounds for microbes that fed on chemistry instead of light. But there's a final, sobering difference. Earth's thick atmosphere and persistent magnetic field protect its surface from much of the sun's harsher output. Mars, having lost its shield, lies far more exposed. Without a strong magnetic field and with only a thin layer of air, its surface is constantly bathed in radiation from the sun and from space beyond. For any life that tried to live openly on the Martian ground, this would pose a serious and continuous challenge, pushing the chances for survival down into the shadows and, perhaps, deep beneath the surface. If life ever found a home on Mars, it may have learned to live out of sight, underground, beneath layers of dust and stone. The world is quieter. Rock and soil act like a blanket, blocking radiation and smoothing out wild changes in temperature. In those sheltered pockets, tiny communities of microbes could have endured long after the surface became harsh and bright. On Earth, we know of organisms such as the bacterium, often called Deinococcus radiodurans, able to survive radiation that would tear ordinary cells apart. It patiently repairs its damaged genetic material over and over, showing just how stubborn life can be. If Mars ever hosted microbes, they might have used similar strategies, tucked into veins of ice or salty brines where radiation cannot easily reach. When we look for early life, Earth gives us something Mars cannot yet match: clear fossils, Ancient stromatolites and microfossils, preserved in sedimentary rock, offered direct proof that microbes were here billions of years ago. On Mars, the search is more delicate. Its surface is constantly sandblasted by wind and bathed in radiation, conditions that slowly erase fragile organic traces. Even so, our rovers are not searching blindly. Curiosity and perseverance carry instruments tuned to find biosignatures, the faint chemical or structural fingerprints that life can leave behind. They linger near clay-rich beds, bright silica patches, and carbonate layers, because those minerals can trap and protect organics. Ancient lake floors and buried sediments are especially promising. If Martian microbes ever existed, their fossils may still be hidden in those quiet layers or preserved below the ground. Over billions of years, Earth and Mars followed very different paths. Earth's crust is broken into plates that drift, collide, and dive back into the mantle. This constant recycling moves nutrients, releases gases, and helps stabilize climate, allowing oceans to remain for a very long time. Mars, smaller and more quickly cooled, has a largely rigid crust. It depended on volcanic outgassing and slow chemical weathering to refresh its atmosphere. As a result, its habitability was probably shorter and more episodic. Periods of flowing water and mild climate, followed by long stretches of cold and dryness. That limited the time available for life to move beyond simple forms. On Earth, life had billions of years to diversify. On Mars, any living things may have remained microscopic, retreating into shrinking refuges as the planet cooled and dried. Yet Mars and Earth might be more closely related than they appear. The idea of panspermia suggests that life, or its building blocks, can travel between planets on rocks blasted into space by impacts. When an asteroid strikes a world like Mars, fragments of crust can be thrown free, carrying with them minerals, organics, and perhaps dormant microbes. Some of those fragments eventually cross Earth's orbit and fall as meteorites. A famous specimen, often called ALH 8401, contains organic molecules and unusual mineral structures that some interpret as possible biosignatures. The evidence is still debated, but the meteorite itself is proof that material from Mars can reach Earth. It raises a quiet question. Did life begin on Mars and then come here? Or did both planets receive the same seeds from elsewhere? From its youth as a warm, wet world to its present as a frozen desert, Mars invites us to rethink what a habitable planet looks like. Perhaps it was a failed experiment, offering life a brief chance it could not hold on to. Or perhaps it was a second cradle, sharing its chemistry and maybe its microbes with Earth before fading into cold. Whatever story we choose, water sits at its center. Liquid water is the lifeblood of habitability. Because water molecules are polar, they can dissolve a wide range of substances and carry nutrients, allowing complex chemistry to unfold. Water's high heat capacity also helps stabilize climates, softening temperature swings and creating gentle environments where life can take root. If life ever existed on Mars, it needed liquid water. That is why so much of our exploration begins with a simple, almost childlike question. Where was the water, and where is it now? Long ago, Mars seems to have worn far more blue than we see today. Geological evidence suggests that vast oceans may once have stretched across its surface. Some estimates suggest that an ancient ocean could have covered roughly 1/5 of the planet, in places plunging to depths of several thousand meters. These waters likely gathered in the northern hemisphere, where broad, low-lying basins form a natural bowl. Under a thicker atmosphere and a warmer sky, waves may have broken along Martian shores, and rivers may have poured into a northern sea. With time, that water retreated. Mars's weaker gravity and thinning atmosphere made it easy for water to escape into space as vapor or to sink underground and freeze. Yet the planet is not truly dry. Radar instruments aboard orbiters, such as the Mars Reconnaissance Orbiter, have mapped large deposits of subsurface ice. Seasonal patterns in the atmosphere show water vapor rising and falling with temperature, hinting at small, ongoing exchanges between soil, ice, and air. The Mars Express mission of the European Space Agency has even reported signs of a buried lake of very salty water beneath the southern polar ice cap. If such a briny reservoir exists, it could provide a rare refuge from the harsh surface, a hidden pocket where liquid water persists even now. Rovers have added their own ground-level evidence. Curiosity has found the rounded pebbles of ancient stream beds in Gale Crater, shaped by fast-flowing water that once tumbled them along the bottom of rivers. Perseverance is exploring Jezero Crater, where a wide river once fanned into a lake and built a delta rich in sediments. Opportunity, during its long journey, discovered small, iron-rich spheres, nicknamed blueberries, which likely formed in liquid water. These detailed close-ups echo the larger patterns etched across the planet. Huge canyon systems, such as Valles Marineris, stretching for more than 4,000 kilometers, networks of dried-up river valleys, and the gentle arcs of ancient deltas. All of them whisper the same thing. Water once moved freely here. Minerals speak the language of water too. Hydrated minerals like clays and sulfates form only when liquid water interacts with rock for extended periods. Their presence across wide areas of Mars shows that water was not just a brief visitor. It lingered long enough to change the chemistry of the crust. Clays point toward relatively mild, neutral, or slightly acidic water, conditions many microbes on Earth would find comfortable. Sulfates reveal episodes of more acidic water, which can still support specialized life. These minerals are not just proof of ancient water. They are some of the best places to look for preserved biosignatures, because they can trap and protect fragile organic molecules. The chemistry of Martian water has changed over time. Early on, it seems to have been relatively fresh in some regions, with salinity levels that would not have troubled many terrestrial microbes. As the planet dried, the remaining water became more concentrated, forming brines far saltier than typical seawater. Today, any small pockets of liquid water that linger underground are likely very salty indeed, more like Earth's hypersaline lakes. The pH of Martian water is thought to have ranged from near neutral to mildly acidic. All of this helps scientists imagine what kinds of organisms might once have lived there and which forms of life could still endure. One of the most precious roles of water is its ability to preserve what it touches. On Earth, sedimentary rocks formed in water-rich environments often contain fossils, chemical patterns, or textures left behind by life. On Mars, similar layered rocks have been identified in ancient lake beds and deltas. If life ever existed there, these sediments may hold its traces, That is why the planned Mars sample return mission is so eagerly awaited. Carefully chosen rocks, brought back to Earth, could be examined with instruments too large and delicate to send across space, finally giving us a chance to look for Martian biosignatures in the greatest possible detail. In its distant past, Mars may have possessed a full hydrological cycle, water evaporating, forming clouds, falling as rain or snow, soaking into the ground, and flowing back toward lakes and seas. Such a cycle would have supported a dynamic climate, with storms and runoff shaping both the landscape and any ecosystems that existed. As the atmosphere thinned and the magnetic field faded, this cycle would have broken down. Rain and rivers faded away, leaving behind ice caps, underground frost, and a surface dominated by cold, dust, and wind. Reconstructing this transition is essential for understanding how long Mars remained hospitable and where its last habitable niches might still lie. The decline from a warm, watery Mars to the dry world we see now is closely tied to atmospheric loss. Without a strong magnetic field to protect it, the upper atmosphere was exposed directly to the solar wind. Over immense time scales, charged particles from the sun stripped molecules away, reducing surface pressure until liquid water could no longer remain stable in the open. High-energy ultraviolet light also helped break apart molecules like water and carbon dioxide, splitting water into hydrogen and oxygen. The lighter hydrogen escaped into space more easily, leaving behind a subtle enrichment of heavier isotopes. Measurements of hydrogen in Martian water vapor today bear that signature, a quiet record of the planet's lost oceans. At first, Mars and Earth had much in common: thick atmospheres, active volcanism, and liquid water. But Earth's larger size allowed it to keep its internal heat longer. Its core stayed molten, powering a magnetic dynamo that still shields our atmosphere. Plate tectonics continued to recycle gases and maintain a long-term climate balance. Mars, smaller and cooling faster, saw its core solidify sooner. Its magnetic field shut down, volcanic outgassing waned, and there was no longer a steady source of gases to replenish the air, being slowly peeled away. Even now, Mars may host small, habitable pockets below the surface. Salty brines locked under rock and ice could remain liquid and shielded from radiation, providing tiny havens for any surviving microbes. On Earth, life has been found in deep underground aquifers, in highly saline lakes, and in ice-bound environments where liquid water exists only in thin films. These analogs keep hope alive that Mars, too, might still harbor life in hidden places. Upcoming missions that drill into the subsurface aim to test this gently, inch by inch. For humans, Martian water is also a promise. One day, it could support explorers and settlers, providing drinking water and raw material for fuel. Beyond practical needs, Mars's water story helps us refine our search for habitable worlds around other stars. It reminds us to look not only for planets with water, but for those able to keep it liquid and stable over long ages. Above all, it shows how delicate that balance can be. Rivers can dry, oceans can vanish, and a once green world can grow cold if its protective layers fail. All of this leads back to the atmosphere that once wrapped Mars in a thicker, warmer embrace. In those ancient days, the planet carried rivers, lakes, and perhaps a broad northern ocean beneath a dense blanket of carbon dioxide and water vapor. That early air trapped heat and allowed liquid water to flow openly across the surface, shaping valleys and filling basins. To maintain such a sky, Mars relied not only on its young climate, but also on the deep fires within its crust. For a long stretch of its early history, enormous volcanoes rose over the landscape, giants like Olympus Mons, breathing out vast amounts of carbon dioxide, sulfur dioxide, and water vapor. These steady exhalations enriched the atmosphere, feeding the greenhouse warmth that made ancient Mars a place where liquid water could linger and where the chemistry of life had room to unfold. As the great volcanoes of Mars slowly fell silent, the planet's ability to keep a thick, warm atmosphere faded with them. Outgassing dwindled, and the sky above began to thin. Today, the air is fragile, but not lifeless. It still shifts and stirs, especially when the seasons wake the dust. From time to time, storms rise on Mars that grow and grow until they wrap around the entire planet. Fine particles of dust are lifted high into the atmosphere, where they mingle with water vapor and trace gases. Up there, sunlight can break apart water molecules more easily, helping the planet lose a little more of its ancient water to space. These storms also cause swings in temperature and pressure, showing how surface and sky remain linked in a delicate dance. They are only distant echoes of the grand processes that once shaped Mars, but they offer a glimpse of an atmosphere that is still evolving, even in its thin old age. At the poles, the story takes on a quieter rhythm. The bright caps there are made of both water ice and frozen carbon dioxide. With each Martian year, a portion of this frozen carbon dioxide turns directly into gas during summer, swelling the atmosphere and slightly boosting surface pressure. In winter, it refreezes back onto the caps, and the air thins again. This slow breathing in and out of carbon dioxide subtly changes weather patterns and reminds us that, despite its stillness, Mars still has seasons and cycles. Beneath the ice and rock, much of the planet's remaining water lies trapped as frozen reservoirs, and some scientists suspect there may still be pockets of liquid brine protected from the harsh surface by layers of insulation. Into this fragile atmosphere, another quiet clue has appeared: methane. Instruments on the Curiosity rover and orbiting spacecraft, such as the Trace Gas Orbiter, have detected tiny amounts of methane that rise and fall with the seasons or appear in sudden small bursts. On Earth, methane often points to life, but it can also be made by purely geological reactions between water and rock. On Mars, its presence in even trace amounts invites questions. Is it produced by buried microbes, by chemical reactions in the crust, or by something else? We do not yet know, but every measurement adds another line to the planet's atmospheric diary. When we compare Mars to Earth, the contrast is striking. Earth's magnetic field and active geology have protected and renewed its atmosphere over billions of years. Plate tectonics cycle carbon dioxide between rocks, oceans, and air, helping keep the climate within a range that can support liquid water. Mars, without global tectonic plates and without a long-lived magnetic shield, could not defend its air in the same way. It lost its sky more quickly, and with it the long-term stability needed for complex life on the surface. That difference helps scientists understand how delicate planetary habitability can be, and how easily an atmosphere can be eroded away on worlds that lack such protections. It also offers a gentle warning. When we look outward to planets around other stars, those that orbit close to their suns without strong magnetic fields may face a fate much like Mars. Future missions will continue to peel back layers of this story. Instruments designed to study subsurface gases, isotopic ratios, and ancient rocks may help us reconstruct the steps by which Mars moved from thick air to thin, from seas to ice. While the air has faded, the rocks remain, and in them we search for signs that the planet was once truly alive. Curiosity, exploring Gale Crater since 2012, has found evidence of ancient lake beds, fine sedimentary layers, clays, and sulfates that reveal long-standing water with gentle, nearly neutral chemistry. Such environments on Earth can be very friendly to microbes. Perseverance, exploring Jezero Crater, roams the remnants of a fossil delta where a river once poured into a lake. By drilling rock cores and studying them, it has detected carbon-based molecules in sediments laid down by flowing water. On our own world, deltas are excellent at trapping and preserving organic material. Jezero is therefore one of the most promising places on Mars to look for subtle biosignatures. High above, orbiters like the Mars Reconnaissance Orbiter map the surface in fine detail and look for the fingerprints of water in the spectrum of reflected light. They have found widespread hydrated minerals such as clays and sulfates, often in ancient basins and valleys. These minerals are formed and altered by water, and they can protect delicate organic compounds by locking them inside their crystal structures. In this way, the crust of Mars acts as a natural archive, preserving hints of past environments. Sedimentary rocks are especially important in that archive. Each layer captures a particular moment in the planet's environmental history. Fine-grained mudstones, identified by both curiosity and perseverance, form in calm waters like lakes and slow-moving pools. On Earth, such rocks are excellent at trapping organic molecules and preserving them for immense spans of time. Their presence on Mars suggests that lakes there were not fleeting. They lasted long enough to allow stable conditions in which life, if it ever appeared, could have settled. Clays add another layer of promise. They form when water interacts with volcanic rock over long periods, gently altering it beyond marking wet conditions. Clays have a special talent. They can absorb and shield organic molecules, preventing them from degrading. On our planet, clays are thought to have helped early chemical systems survive and combine. On Mars, they may have played a similar protective role, preserving traces of any biology that once touched them. Some of the most controversial clues come from Martian meteorites found on Earth. The meteorite known as ALH 8401, discovered in Antarctica, contains tiny structures that some scientists have compared to fossilized nanobacteria. It also hosts magnetite crystals arranged in ways that resemble certain biological patterns seen in terrestrial bacteria. Others argue that these features can arise from non-living chemistry. The debate remains unresolved, but the meteorite still intrigues researchers because it shows how subtle and ambiguous possible biosignatures can be. Perseverance has begun to notice rock textures on Mars that look a little like stromatolites, layered structures on Earth, built by microbial mats that trap and bind sediments over time. These Martian formations may turn out to be purely geological, but their resemblance to known biosignatures makes them prime targets for closer study. To help interpret them, scientists compare them to stromatolites found in ancient places on Earth, such as Shark Bay in Australia. Those earthly structures, among the oldest known signs of life, give us a template for what to look for on Mars. Chemistry offers another set of tools. On Earth, life often leaves its mark in the ratios of isotopes, different forms of elements like carbon and nitrogen. Biological processes can favor one isotope over another, creating patterns that stand out from those made by simple chemistry. On Mars, Rovers have measured variations in isotopes, including in methane, which has sparked discussions about whether these patterns hint at biological activity or can be fully explained by geology. Methane is especially tantalizing because so much of it on Earth is made by living organisms, yet every possible sign on Mars comes wrapped in uncertainty. Many processes that do not involve life can still generate organics, layered rocks, and isotopic patterns that look deceptively biological. Distinguishing between these abiotic signals and true biosignatures is a central challenge. On top of that, there is the persistent concern about contamination. Even with careful sterilization, there is always a small risk that Earth microbes could hitch a ride on a spacecraft, or that terrestrial organics could mix with Martian samples. This is why plans for returning rocks from Mars to Earth involve strict containment and extremely clean laboratories. Mars's surface today is also a difficult place to preserve anything delicate. Radiation, cold, and the lack of a protective magnetic field all work against the survival of organic molecules at or near the surface. This is one reason why scientists are so interested in the subsurface. Just a few meters down, conditions may be much kinder, and biosignatures could be better preserved. Future missions may carry drills capable of reaching deeper layers, especially in regions that show signs of past hydrothermal activity. On Earth, hot springs and vents support rich ecosystems. On ancient Mars, similar environments may have been hotspots for early microbial life. One day, humans may walk those terrains themselves. Astronauts, able to move quickly, choose targets on the spot, and adapt their plans in real time, could greatly accelerate the search for signs of life. They would bring not only their own senses and judgment, but also advanced field instruments that can be used flexibly in ways robots cannot easily match. Until then, the rovers that bear the name Perseverance and the people who guide them carry our quiet determination forward, a patient effort to understand whether Mars was once truly alive. As we weigh all these hints, it is natural to look sideways at another world and ask why Mars, and not Venus, has become our main focus in the search for ancient habitability. Venus and Mars could hardly be more different today. Venus is a world of crushing pressure and furnace heat, its surface hotter than molten lead, wrapped in carbon dioxide and clouds of sulfuric acid. Mars is cold, thin, arid, and barren, yet long ago, both may have held promise. Venus might once have worn shallow oceans and a gentler climate, with abundant sunlight and a thick carbon dioxide atmosphere. It may have balanced just long enough for water to pool on its surface and for simple chemistry to flourish. But its closeness to the sun meant relentless heating. As more water evaporated, water vapor itself trapped additional heat, a powerful greenhouse gas feeding a runaway loop. Oceans boiled away, releasing even more carbon dioxide. Without liquid water to help regulate the climate, the spiral continued. Ultraviolet light from the sun broke apart water molecules in the atmosphere, letting the lighter hydrogen escape into space and leaving Venus permanently dry. Its carbon dioxide blanket thickened and thickened until the surface became the hottest in the solar system. Mars, by contrast, began farther from the sun, receiving less light and heat. Even so, evidence of old riverbeds, deltas, and lake basins shows that for a time, its temperatures and atmosphere were just right for liquid water to remain on the surface. A thicker, early atmosphere, heavy with carbon dioxide, helped to warm the planet despite the weaker sunlight. But Mars carried its own disadvantage: its small size. being much smaller than Earth and Venus. It lost its internal heat more quickly. Its magnetic field faded, its tectonic vigor waned, and its ability to keep a dense atmosphere gradually slipped away. Solar winds stripped off its air, and much of its water either froze or vanished into space. In the end, while Venus became too hot, Mars became too cold. This contrast is sometimes called a kind of Goldilocks problem. One planet went one way, the other another, leaving Earth in between. Venus and Earth are almost twins in size and mass, which helps them retain atmospheres and maintain internal heat. Their geology can recycle carbon dioxide into rocks and release it again, helping steady the climate over immense timescales. Mars, about half Earth's diameter and holding only a small fraction of its mass, simply could not do the same. Its weaker gravity made it easier for gases to escape, and its smaller interior cooled faster, halting the deep processes that might have renewed its atmosphere. Today, Venus's atmosphere presses down with a surface pressure about 90 times that of Earth, trapping heat in a permanent, intense greenhouse. Mars's atmosphere, by contrast, is less than 1% of Earth's surface pressure, made mostly of carbon dioxide, but far too thin to hold warmth. It cannot shield the surface well from radiation, and it cannot keep water liquid in the open. The different fates of these two planets show how both too much atmosphere and too little can erase habitability. Distance from the Sun plays its part as well. Venus circles at about 0.72 astronomical units on the inner edge of the Sun's habitable zone, bathed in nearly twice the solar energy that Earth receives. Mars orbits at about 1.52 astronomical units on the outer edge, receiving far less light. For Venus, that closeness helped drive the runaway greenhouse that destroyed its oceans. For Mars, the greater distance meant that once its atmosphere thinned, there was not enough energy to keep it warm and wet. Taken together, these diverging stories gently underline how important a planet's position is within the habitable zone, not just whether it lies inside it, but where and with what protections and internal strength it carries into that fragile band. Venus shows us what happens when a world stands too close to its star, while Mars reveals the quiet danger of drifting too far away. Venus is still geologically active. Spacecraft have seen signs that some of its volcanoes may still erupt, sending fresh carbon dioxide into an already suffocating sky. With no plate tectonics to tuck that gas back into the crust, the carbon dioxide simply piles up, feeding a greenhouse effect that never ends. The planet has no way to breathe in again, no gentle cycle to soften its own heat. Mars, in contrast, has fallen mostly silent. Its great volcanoes, including giants like Olympus Mons, are now cold monuments to a more active time. When the interior cooled and eruptions faded, the outgassing of greenhouse gases dwindled. With fewer fresh gases to replenish the thinning air, the atmosphere continued to slip away. Without deep geological cycles to recycle and regulate key elements, Mars found it harder and harder to support the complex, self-sustaining systems that long-term life seems to need. Together, the fates of Venus and Mars sketch out the edges of a fragile window. One world shows how a climate can run away into unbearable heat when there is no way to pull greenhouse gases back down. The other shows how a planet can slowly starve of air and warmth when it is too small and too exposed to keep its atmosphere. For scientists searching the skies for distant worlds, these lessons are precious. When they study exoplanets, They look not only at distance from the star, but also at size, atmospheric makeup, magnetic protection, and whether there might be enough geological activity to keep a climate in balance. The stories of Mars and Venus remind us that habitability is not a single switch, but a delicate equilibrium. Even knowing all this, there is a softer, more intimate question that lingers around Mars. Is anything still alive there now? The discovery of living organisms on the red planet, even the simplest microbes, would change our understanding of life forever. It would show that biology is not confined to Earth, but can arise wherever conditions cross some quiet threshold. If Martian life is truly independent, built from a different origin than life here, it would be our first glimpse of a second Genesis. If, on the other hand, Martian microbes turn out to share deep genetic patterns with us that would strengthen the idea that life can travel between planets, perhaps carried in rocks and ice. Either way, living cells from Mars would give us something we have never had before. Another example of life to place beside our own. We could ask how it copes with cold, dryness, low pressure, and high radiation. We could ask what it needs and what it can do without. Our picture of what is possible for biology would widen, and ideas that once felt like speculation would suddenly sit solid on a petri dish. The search for such life has gathered momentum as our robotic explorers grow more capable. Perseverance, rolling slowly across the ancient delta of Jezero crater, was built with astrobiology in mind. Jezero is the remnant of a river system that once poured into a lake, spreading sediments like a fan. On Earth, deltas are good at catching and preserving organic material, so Jezero is one of the best places on Mars to look for hidden biosignatures. Perseverance carries a suite of sensitive instruments, including one named for its careful attention to detail, designed to scan rocks with lasers and light to detect organic molecules and textures that might hint at fossilized microbes. Another rover, from a partnership between the European Space Agency and Roscosmos, is planned with a different advantage. A drill capable of reaching roughly 2 meters below the surface. Down there, rocks and any organic molecules they contain are better shielded from radiation and chemical breakdown. That rover will carry its own organic molecule analyzer to sniff out complex carbon-based compounds and study their structure. At the same time, Curiosity continues its slower, deeper work in Gale Crater, focusing on ancient habitability. By examining mudstones and mineral layers from old lakes, it helps us understand where life could have thrived, even if it no longer does. Finding life is far from simple. The Martian surface is bathed in radiation, and many organic molecules break down over time. That is why subsurface drilling is so important. Beneath the top layer of dust and rock, conditions are calmer. Biosignatures, if they exist, stand a better chance of surviving. On board the rovers, spectroscopic tools shine light on powdered samples and read the returning glow, revealing which molecules and minerals are present. Some of these instruments can tell apart organic compounds that are likely to be biological from those that probably formed through purely chemical processes. Above the ground, atmospheric studies add another piece to the puzzle. Variations in methane levels over Martian seasons suggest that something, somewhere, is making and releasing this gas. Orbiters like the Trace Gas Orbiter examine the atmosphere with exquisite sensitivity, looking not only at methane, but at the isotopic fingerprints of carbon and oxygen within it. Those subtle patterns might hint at whether the gas comes from geological reactions or from metabolism. If life persists on Mars today, it is most likely hiding in places where conditions remain relatively stable and some form of liquid water still exists, even if only briefly or in small amounts. Subsurface brines are a prime candidate, salty pockets of liquid that can stay unfrozen at temperatures where pure water would turn solid. Radar hints at such briny lakes beneath the southern polar ice cap, and these regions have become high on the wish list for future missions. The polar caps themselves may preserve ancient organisms, if any ever live there, frozen layer upon layer like pages in a book of ice. Caves and lava tubes offer another quiet refuge. These hollow spaces, carved by past volcanic flows or erosion, are shielded from direct radiation and extreme temperature swings. If ice or brine has collected inside them, they could provide small, stable environments for microbes. Then there are the recurring dark streaks that appear on some Martian slopes in warmer seasons. Their exact nature is still debated, but if they do involve thin flows of briny water, they would be important sites to study with great care. To truly answer the question of extant life, we will likely need to bring Mars to Earth. In a sense, the Mars Sample Return Effort, a collaboration between NASA and the European Space Agency, aims to retrieve carefully cached rock cores collected by Perseverance and deliver them to laboratories on our own world. There, using instruments that are too large, delicate, or complex to ever fly, scientists will look for tiny fossils, complex organics, and isotopic signatures that could indicate life. Human explorers someday may take this further. Astronauts on the surface could travel quickly to diverse sites, drill deeper than robots, and adjust their plans in real time based on what they see and measure. As we move toward that future, new missions are being designed to map subsurface ice, refine images of promising terrains, and chart where water, shelter, and interesting chemistry are most likely to be found. Some of this work is practical. Ice will be a key resource for any long-term human presence, but woven through it is a deeper intention to find out whether Mars is, or ever was, a living world. If we do find life there, new questions will follow close behind. How do we protect a second biosphere from contamination by ours? How do we avoid carrying Martian microbes back home in ways that might disrupt delicate ecosystems here? Planetary protection becomes not just a guideline, but an ethical obligation. At the same time, finding life would strengthen the case for Mars as a place where humans might one day build lasting settlements, drawing on local water, fuel, and perhaps even insights from native organisms. Behind all of this lies the broader story of how Mars and Earth parted ways. From the beginning, Mars was at a disadvantage. Its smaller size meant weaker gravity, making it harder to hold on to an atmosphere as solar wind and radiation nudged lighter particles into space. Over countless millions of years, hydrogen and helium slipped away, followed by gradual losses of other gases. Each bit of erosion left the planet a little more bare. Small worlds also cool faster, while Earth's core remains molten enough to power vigorous volcanic activity and a strong magnetic dynamo. Mars's interior solidified relatively early. Its magnetic field faded, and without that protective bubble, the upper atmosphere stood exposed to the sun's charged particles. Spacecraft like Maven have watched this stripping process in action, seeing how the solar wind continues to carry off Martian air even now. The result is a thin, mostly carbon dioxide atmosphere that struggles to trap heat or support liquid water on the surface. Earth tells a different tale. Its magnetic field generated by the constant motion of liquid metal in the outer core, deflects much of the solar wind, preserving the atmosphere. Tectonic plates slide, collide, and dive, reshaping continents, lifting up mountains, and driving a long-term carbon cycle. Volcanic eruptions release carbon dioxide into the air, while subduction carries carbon-rich rocks back into the mantle. This dynamic balance has helped Earth avoid both a runaway greenhouse and a deep freeze, keeping conditions suitable for life over astonishing spans of time. Mars, lacking such plate tectonics, has a surface that is more like a frozen snapshot. Features like Olympus Mons, the tallest volcano we know in the solar system, speak of intense volcanic activity long ago, but they also remind us how long that activity has been quiet without moving plates. There is no efficient way to recycle carbon dioxide, no ongoing reshaping of the crust to create diverse environments, no steady renewal of a protective atmosphere. Earth's magnetic field does more than protect its air. It also shields the surface and the organisms living there from harmful radiation, providing a stable stage on which complex life can evolve. Mars, once its field faded, had no such shield. Radiation from the sun and from deep space reaches the surface much more easily, making it a harsh environment for delicate biology. Any surviving life would have been forced into protective niches underground, under ice, or within rocks. Both planets once shared a watery youth. Mars shows clear signs of rivers, lakes, and perhaps oceans, just as Earth does, but where Earth's water cycle still turns, clouds forming, rain falling, rivers flowing to seas. Mars has largely ground to a halt. Its remaining water is mostly locked as ice in polar caps and underground deposits, with only thin traces moving through the atmosphere. The dry riverbeds and layered sediments we see there are memory, not active process. In its early days, Mars was geologically alive, its volcanoes erupting with energy, reshaping the land, and pumping gases into the sky. Those eruptions likely helped build the greenhouse blanket that once made liquid water possible. As the interior cooled and that volcanic fire faded, the planet lost a vital source of atmospheric replenishment. Earth, bigger and warmer inside, still experiences frequent volcanic activity. That ongoing geological vitality not only helps maintain the atmosphere, but also creates diverse habitats, from deep-sea hydrothermal vents to rich volcanic soils on land where life can take hold and quietly thrive. All of this rests on something quiet but powerful: the way a planet moves carbon in and out of its air. On Earth, the carbon cycle gently controls the greenhouse effect, keeping our climate mild enough for oceans to stay liquid. Volcanic eruptions, weathering rocks, growing forests, and subducting plates all take turns in a slow, balancing dance. Mars did not have that luxury for long. As its atmosphere thinned and its heat leaked away, its greenhouse blanket collapsed. The surface cooled, the last lingering water vapor condensed and froze, and the planet drifted into the icy desert we see today. The difference between the two worlds is like a narrow line, a reminder of how finely tuned habitability really is. The sun's light carries the same double edge everywhere. Mars, farther out, receives less energy, which helps explain its colder climate. Earth, in the comfortable middle of the habitable zone, gets just enough warmth to support liquid water and a stable climate most of the time. Yet that extra distance once gave Mars a brief advantage. Unlike Venus, It was spared a runaway greenhouse, and for a while, that allowed rivers, lakes, and perhaps small seas to exist under a thicker sky. In the early days, both Earth and Mars were battered by asteroids and comets. These impacts scarred their surfaces, but also delivered water and organic molecules. Earth, wrapped in a denser atmosphere and powered by vigorous tectonics, could recover more easily. Craters eroded, new crust formed, and life eventually found its way into the oceans. Mars, with its thin air and geologically quiet surface, had a harder time healing. Damage lingered, and its limited ability to rebuild may have further narrowed its window for development. It is tempting to imagine a slightly different Mars. If it had been just a little larger or a bit closer to the Sun, with stronger gravity and a more long-lived magnetic field, it might have held on to its atmosphere and water much longer. Perhaps it could have grown forests of its own or oceans with complex ecosystems. Instead, its path diverged, and that divergence has become one of our greatest teachers about how size, distance, geology, and air all weave together to make a world welcoming or not. One of the most intriguing questions that grows from this story is whether Mars might have helped us begin. Mars and Earth share a special relationship, two siblings circling the same star, shaped by many of the same early events. Among the ideas about life's origin, one quiet possibility suggests that Mars, with its early head start, may have been the first to spark life and then gently pass that spark to Earth. Picture the young solar system, noisy, crowded, full of collisions. Asteroids crashed into forming planets, blasting material into space. Because Mars has weaker gravity and a thinner atmosphere than Earth, fragments of its crust could be thrown free more easily. Some of those fragments would wander through space until they crossed Earth's orbit and fell as meteorites. In that scenario, rocks containing Martian microbes, safely shielded inside, might have made the journey between worlds. We know that pieces of Mars have indeed reached Earth. Meteorites, such as ALH 8401, carry chemical signatures that match the Martian atmosphere. They are, in a very real sense, stones from another world lying in our deserts and on our ice. Inside some of them, scientists have found organic molecules and puzzling structures. One meteorite in particular sparked debate when tiny shapes inside it were compared to possible microfossils, and its magnetite crystals were found arranged in patterns that looked faintly biological. The evidence is not clear enough to prove ancient Martian life, but it shows that these rocks can preserve subtle clues for billions of years. If life were to ride such a meteorite, it would face a hard road, the shock of ejection, the cold and radiation of space, and the heat of re-entry through Earth's atmosphere. Yet on our own planet, we have discovered extremophiles that hint at how this might be possible. Microbes like the bacterium, often called Deinococcus radiodurans, can survive intense radiation and repair their damaged DNA. Tardigrades, the tiny water bears, can enter a dry, dormant state and endure vacuum, cold, and heat that would kill most other creatures. Laboratory experiments simulating impacts, space conditions, and atmospheric entry suggest that microbes buried deep inside rocks can sometimes survive each stage. It is not a gentle journey, but it is not impossible. Mars may also have had an early advantage in timing. Being smaller, it cooled faster after its formation. That allowed a solid crust and liquid water on the surface to appear, while Earth was still largely molten and hostile. For a time, ancient Mars had rivers, lakes, and perhaps an ocean beneath a thicker atmosphere and a protective magnetic field. Volcanic activity would have supplied heat and nutrients. In that era, Mars might have been more welcoming to emerging life than Earth was. During the period often called the Late Heavy Bombardment, material was swapped between planets with surprising efficiency. Models suggest that huge amounts of Martian rock could have landed on Earth over long spans of time. If even a tiny fraction of those rocks carried viable microbes, the odds of seeding would no longer seem so distant. In that picture, life could have begun on Mars and later taken root in Earth's more stable, long-term environment. There are, of course, thoughtful counter-arguments. Earth itself is a strong candidate for the origin of life. Deep-sea hydrothermal vents, rich in minerals and chemical energy, offer a natural setting where simple molecules could assemble into something living. Earth's abundant water, ongoing tectonics, and lasting magnetic field created a robust, varied environment where life could arise and flourish without help from elsewhere. Some scientists point to the sheer diversity of Earth's biosphere as a sign that it grew from a local beginning, shaped over time by this dynamic planet. To tease these possibilities apart, we look again to Mars. Perseverance, exploring the ancient lakebed of Jezero Crater, is searching for signs of fossil microbes in sediments that were once underwater. It is also collecting rock cores that will be sealed and, if all goes well, brought back to Earth by a future Mars sample return mission. In carefully controlled laboratories, we will examine these samples for complex organics, tiny fossil structures, and isotopic patterns that could indicate life. If we find clear signs of Martian biology, we will be able to ask whether it resembles life here closely enough to hint at a shared origin, or whether it is truly different. Whatever the answer, the discovery of Martian life would change our story. If it turns out that Earth life began on Mars, the red planet would become the elder sibling in our biological family tree, the first cradle from which our lineage stepped. If, instead, life arose independently on both worlds, then life would seem far more common and natural than we once dared to imagine. Two separate beginnings in one small solar system would suggest a universe where life is not a rare accident, but something that happens whenever conditions allow. Such a discovery would not only touch science, it would reach into ethics as well. If there is still life on Mars, even in the form of tiny microbes, we would have to ask how we should behave toward it. Sending humans, building bases, or changing the environment would no longer be a simple engineering question. We would need to balance our urge to explore and settle with a responsibility to protect another biosphere, however small. International agreements already speak of preventing contamination, but they were written when Martian life was mostly a distant possibility. New guidelines might be needed to honor the rights of an alien ecosystem, even if its inhabitants are microscopic. Mars's history, whatever we find, could also hold a mirror up to Earth's future. If it once had thriving life that later disappeared, the reasons for that decline, loss of magnetic field, stripped atmosphere, cooling interior, would carry important lessons about planetary fragility. If, instead, Mars is found to be lifeless, despite once having the right ingredients, that too would teach us about how narrow the path to life may be. And beyond the scientific and practical questions, there is a quieter layer still. Discovering life on Mars would ripple through spiritual and religious traditions across the world. Many stories have placed Earth at the center of living creation. Evidence of life on another planet would not erase those stories. but it might ask them to stretch. For some people, the realization that life exists not only on Earth, but also on another world would feel unsettling. For others, it might deepen a sense of wonder that whatever shaped the universe chose not just one place for life to bloom, but many. For some people, the idea of life on Mars would feel like a soft expansion of faith, a wider sky above the same beliefs. For others, it might gently unsettle Earth-centered views, nudging old stories to stretch and make room for worlds beyond our own. It could also do something quieter and more beautiful. Remind us that whatever we believe, we are sharing a universe far larger than any single tradition. Knowing that life exists on more than one world might invite a sense of humility and a deeper kind of kinship, not just with other humans, but with all living things. In that way, Martian life could become less a threat to our identity and more a bridge, a reminder that we are traveling together through a vast, interconnected cosmos, and that our differences are small beside the distances between stars. Instead of dividing us, such a discovery could become a gentle mirror, reflecting back a simple truth. We are all participants in a much bigger story. It would also mark a turning point in that story, the moment we find life beyond Earth. Even a single microbe is the moment we stop being strictly a one-world species. Our responsibilities would suddenly feel larger. Interacting with an alien biosphere, even cautiously, would ask us to think of ourselves not only as explorers, but as caretakers. Our choices would echo between planets. Mars would quickly become more than a scientific target. It would seep into art, music, novels, and philosophy, just as the first footsteps on the moon once did. Poets would ask what it means to share a universe with Martian life. Children would grow up imagining not only astronauts on a red horizon, but perhaps strange microbes curling in brine beneath the ice. Stories of coexistence would widen to include not just other cultures, but other forms of life entirely. If life began on Mars and later seeded Earth, our own history would be gently rewritten. Human and biological stories would gain a new first chapter, set under a colder sun. Life would stand revealed as something that can endure violent impacts, vacuum, radiation, and the long dark between worlds. Mars and Earth would no longer feel like isolated spheres, but like two knots tied in the same cosmic thread. Even if life arose independently on both planets, the message would be just as profound. Two worlds in one small solar system, finding their own paths to biology, would imply that life is not some impossible accident. It would hint that wherever rocks, water, energy, and time come together in the right way, there's a chance for chemistry to wake up and begin to copy itself. Our search elsewhere would change accordingly. Moons like Europa, Enceladus, and Titan would draw even more attention. Icy shells hiding deep oceans, or thick atmospheres rich in complex chemistry. Exoplanets around distant stars, especially those in gentle orbits with the right temperatures, would become more than dots of data. Mars would serve as a template for asking the right questions. Where is the water? How stable is the climate? Is there a protective magnetic field? Are there signs that carbon chemistry has moved beyond simple molecules? Technologically, every step we take on Mars feeds back into this wider quest. The drills designed to reach deeper, searching for buried biosignatures, will someday be adapted for other worlds. Instruments that can sniff out faint patterns in isotopes or distinguish subtle organic structures will follow us into the outer solar system. Meteorites from Mars, still falling now and then onto Earth, will keep offering hard, cold samples of a world that once may have breathed and flowed in ways more familiar than its present face suggests. Mars also invites us to think about connection in a new way. If life exists, or once existed, on both planets, perhaps they are not entirely separate stories. They might be nodes in a shared biological network, exchanging material and possibilities in slow, patient arcs over deep time. Even the extinction of Martian life, if that is what happened, would have something to say. It would underline how delicate a biosphere can be, how easily the conditions that support it can be lost. For future generations, the consequences would be lasting. Finding life on Mars would encourage long-term investment in science, education, and exploration. The red planet would stand as a symbol of what can be achieved when people pool their curiosity and resources across borders, but it would also press deeper questions on us. Are we primarily stewards of life, wherever we find it, or are we explorers first, willing to reshape other worlds in our own image? How do we balance those roles? Mars sharpens another question as well. Who are we exactly? If our biological roots trace back to the red planet, then, in one sense, we are Martians, looking back at our place of origin across the gap of space. Our identity as purely Earthborn beings would soften. Being human would mean belonging to more than one world. Even if we did not begin there, the possibility alone invites us to think of ourselves as part of a larger tapestry woven from many planet stories. Not just one. It also nudges us toward old, persistent mysteries. Are we here because of a fragile chain of chance events, each one barely succeeding, or because life is a natural, almost inevitable outcome when the universe has matter, time, and energy to play with? Mars may not give final answers, but it can offer clues in its rocks, in its lost air, in the presence or absence of fossils hiding in ancient lakes. The idea of a great filter hovers quietly above all this, a hypothetical barrier that might explain why we have not yet heard from advanced civilizations. If Mars once hosted life and then lost it, its story might reveal how hard it is for any biosphere to survive long enough to become technological. Or it might show us that early hurdles can be overcome and that the real challenges lie further ahead in how intelligent life treats its own world. In that sense, Mars is not only a scientific case study, it is a kind of mirror. Its dried riverbeds and empty basins reflect back questions about our own planet's future. Its silence asks us to think about what it takes to keep a world alive and what happens when the balance slips. The journey to understanding Mars is far from finished. Missions now in flight and others still being designed will push our perspective outward. The Mars sample return effort, weaving together orbiters, landers, ascent vehicles, and return capsules, aims to bring small pieces of the planet's surface into our laboratories. There, using instruments that fill entire rooms, we will look for the faintest signs of ancient cells or complex organics, and for the subtle chemical signatures that only biological processes tend to leave behind. Rovers, like the one named for Rosalind Franklin, will seek their clues underground, drilling down to depths where radiation cannot easily reach. By sampling older, protected layers, they may find biosignatures preserved far better than anything near the surface. Other nations are crafting their own sample return plans, adding more perspectives and more chances to touch Martian rock directly. New orbiters will survey subsurface ice, mapping out reservoirs that may have sheltered life and could someday support human explorers. Private spacecraft designs are being tested and refined with an eye toward carrying people and cargo to the Martian surface. Even if their primary goal is building habitats, every landing will also be an opportunity for science, a chance to deploy new instruments, explore caves, reach polar regions, and walk across terrains that no rover could safely navigate. On Earth, scientists refine their tools in places that resemble Mars in small, harsh ways. In the cold deserts of Antarctica, in the driest stretches of the Atacama, in polar valleys scoured by wind and ice, they test drills, sensors, and sampling techniques. Meteorites from Mars are sliced, polished, and examined, each one a tiny fossil of the planet's volcanic, atmospheric, and chemical past. At some point, human footsteps will likely join rover tracks on the Martian dust. Astronauts will bring agility and intuition, able to change plans in a moment, follow a promising outcrop on a hunch, or carefully work with fragile samples that machines might damage. They will be able to drill deeper, stay longer, and run experiments on site. With portable laboratories, Mars will become not just an object of study, but a place where people live and work. Because Mars is relatively close, it is also a rehearsal space for journeys beyond. The challenges of surviving its cold, thin air, its isolation, and its distance from Earth will teach us how to venture further out to the icy moons and beyond. Its lower gravity might one day make it a natural launch point for missions to the asteroid belt or to the far reaches of the solar system. Telescopes placed on its surface, free from Earth's weather and air, could watch exoplanets and galaxies with startling clarity. Through all of this, Mars continues to be a kind of lantern for human imagination. For thousands of years, it has appeared in myths and stories as a god of war, a wandering star, a mysterious neighbor. Now it stands as a shared goal that encourages cooperation between nations and inspires countless young minds to study the sciences and arts that make exploration possible. At the same time, its barren plains and lost water are a quiet warning. They remind us that planets can change, atmospheres can be stripped away, and habitability is not guaranteed. In learning what happened to Mars, we gain insight into how to care for Earth, how to keep our own air, water, and climate within the gentle bounds that life needs. In the end, every question we ask about Mars is also a question about ourselves. Could life have started there and found its way here? Could there be other worlds, circling other stars, where rivers once ran and tiny cells once divided? The red planet sits nearby, holding evidence in stone and ice, inviting us to look closer. With each mission, each sample, each new image of a ridge or a dry delta, we move a little nearer to understanding whether life is a lonely flicker or a common light scattered across the galaxy. Whatever we discover, Mars has already altered the way we wonder. It has shown us that another world can be both familiar and alien, both promising and desolate. As we continue to listen to its silent landscapes, we may find not only traces of ancient microbes, but also a clearer sense of who we are, where we came from, and how many other stories might be unfolding under distant suns.